Hello everyone, this session we are going to discuss about the application of Rolle's theorem in solving equations. Those equations may be polynomial equations, equation may be transcendental equation. Like if we consider the graph of this polynomial, all of you can see that this polynomial has 1, 2, how many roots I am going to tell you. This polynomial equation has number of roots 1, 2, 3, 4, 5. How to draw conclusion from the graph? Because root or zeros of polynomial means the point of intersection of its graph with the x-axis. So this polynomial graph intersects x-axis at 5 points. So there are 5 roots of the polynomial. Now, if I tell you Rolle's theorem is applicable between these 2 points. These 2 points I don't know exactly. These 2 points we can find from the graph, but we are not interested to find it now. These are 2 points on the graph. Between these 2 points, there are some more points where tangent will be parallel to the x-axis. So this is one of the point. This is one of the point. It means other points also there. Point lies here. Yeah. So these are 4 points where you all can see that tangent is going to be parallel to the x-axis. It means slope of tangent at a point is given by f dash x. Means at those 4 points be C, D, E and F. These 4 points f dash x is equal to 0. Now f dash x equal to 0 is an equation. This equation will be satisfied at this point, here and here also at these 4 points. Now can't I say that Rolle's theorem, if it is valid between 2 points A and B, then this equation f dash x equal to 0, function is fx, its derivative equation is f dash x equal to 0. It is satisfied at these 4 points C, D, E and F. It means the derivative has 4 roots between 2 points A and B. Derivative is f dash x equal to 0. So between 2 successive zeros, there must be at least 1 zero. And this is actually stated in Rolle's theorem. If a function fx is continuous in a closed interval AB, number 2 differentiable in an open interval AB, and fa equal to fb, then the theorem states that there exists at least one point C which belongs to this interval such that derivative at that point equal to 0. So in this graph you can see that those points are actually x-coordinate of this point C, D and E and F. These 4 points, the tangent is parallel to x-axis. Those 4 point x-coordinate will satisfy this equation f dash x equal to 0. So Rolle's theorem can be used to find the root of derivative of polynomial equation. Or we can say that if a polynomial fx has 2 roots alpha and beta, then f dash x has a real root gamma, where gamma lying between alpha and beta, then derivative at gamma must be equal to 0. I mean f dash gamma is equal to 0. Clear? So polynomial has 2 roots at alpha and beta. then there exists at least one root gamma of f dash x. Gamma obviously lies between alpha and beta, where derivative at that point vanishes. And derivative at the point gamma is equal to 0. That is, f dash x has a root at that point gamma. So this is the concept of Rolle's theorem, which can be used to predict root of f dash x equal to 0. Or one can say that if there are two conjugative roots of polynomial fx, these are two conjugative roots, those roots be alpha and beta, then according to Rolle's theorem, there is a root gamma where f dash x equal to 0. This is the root of f dash x equal to 0 only. Gamma is the root of f dash x equal to 0. So between two successive roots of fx equal to 0, there is a root of fx, there is a root of f dash x equal to 0. This is very important. Just suppose they have asked you to find. Now, when you are going to predict something about an equation, you remember that equation should be given in the form f dash x. But you need to check the condition of Rolle's theorem on fx, not on f dash x. Equation given in the form f dash x. You need to get it in the form, you need to get fx from f dash x, then check whether Rolle's theorem conditions are applicable over there or not, and then only we can say that f dash x equal to 0 has a root between two conjugative roots of fx equal to 0. We will discuss more about it. Let us see how this concept can be applied to this equation. Show that, suppose question arises this manner, show that the equation sin x minus x cos x equal to 0 has a root between 0 and 2 pi. So I told you this thing going to be f dash x. What is fx? How do we get fx from f dash x? We can get it by integration. So what we need to do there, we need to find the original function fx from f dash x. So we are answering this manner. Let f dash x be the given equation. Sin x minus x cos x. So how do I get fx from here? To get fx, we integrate this expression. Sin x integration minus x cos x dx integration. Sin x integration you all know minus cos x. And this is going to be what? This is going to be, by parts if you apply, it is 1 into sin x. I mean x into integration of cos x is sin x minus 1 into integration of cos x is sin x dx. Plus c will be there. So this is changed to minus cos x minus x sin x, and this one is minus cos x. This is coming sin x. Sin x is minus cos x plus c. Okay. But this question, it is better you take sin x plus x cos x. Otherwise that condition will not be satisfied here. So I am changing a bit here. This will be plus and this is minus sin x, it will be plus. So this is changed to x sin x plus c. So if we take the function fx equal to x sin x plus c, then this function is always continuous everywhere, this function is differentiable everywhere, and f0 equal to f2 pi. Why? Because here f0 will be 0 plus c, f of 2 pi also 0 plus c. So both are becoming equal to c. f0 equal to f2 pi. So what will be your conclusion here? All three conditions of Rolle's theorem satisfied, because the function we got x sin x plus c. X is continuous differentiable everywhere, sin x also continuous differentiable everywhere, so their product plus another constant must be continuous and differentiable. So first two conditions of Rolle's theorem satisfied on fx. This condition also satisfied because f0 is becoming c, f2 pi is also c. That is f0 equal to f2 pi. So if we are taking this function fx equal to x sin x plus c in the interval 0, 2 pi, it is continuous. In the open interval 0, 2 pi, it is differentiable. And also we got f0 equal to f2 pi. What is going to be your conclusion now? Your conclusion will be that, now we will say that since all conditions of Rolle's theorem is satisfied, therefore f dash x is equal to sin x plus x cos x has a root between zero and 2 pi. This was the question they have asked. Now let us start solving few more questions based on the concept we have just learned from Rolle's theorem. So for this one, suppose they have asked you to prove this equation fx equal to x cube minus x square minus x plus 1. There is a root of this equation, there is a root of its derivative on the interval minus 1 to 1. So this is a comparatively easier question. They are telling the function and they are asking about its derivative. So we will work on this first. How to state that this number 1 fx equal to x cube minus x square minus x plus 1 is a polynomial function. This is continuous in minus 1 1, no issue. It will be continuous because it's a polynomial function. Polynomial functions are everywhere continuous. They are everywhere differentiable also. So differentiable in minus 1 1. And number 3, that f of minus 1. F of minus 1 is minus 1 plus 1 plus 0. And f of 1, if you calculate, it is going to be 1 minus y square minus 1 plus 1. This is also 0. Okay. So all three conditions of Rolle's theorem satisfied on this polynomial equation. And the question was to check whether the derivative of this equation has a root between minus 1 and 1 or not. You tell me whether you have got the answer or not. Because it's derivative, they are talking about derivative. So if we consider that we have proved fx continuous, shown fx differentiable, we have got one additional thing, that is f of minus 1 equal to f1. So we can say that, so the function polynomial function fx has a root between minus 1 and plus 1. Similarly, we can get it for the next equation, that fx is given find the number of real roots of this equation. This is a very beautiful application is there for this one. Very good application. If you start thinking, you will see that this kind of sum is not solved before. But you can do it easily with the help of Rolle's theorem concept. If fx equal to this, then find the number of real roots of f dash x equal to 0. There are two ways to get. One is just by algebraic application of Rolle's theorem, the way we do it previous sums. And another method is that we will remember that between two successive zeros of fx, there is a root of f dash x. Am I clear? Between two successive roots of fx, there is at least one root, not one root, at least one root of f dash x. No, don't take the graph where there is a king. You better change the graph. You change the graph this manner. Just a minute. This is done already. We don't need any more. Just let us prove this one. So how to prove that? How to find the number of roots of f dash x equal to 0? They are talking about fx. So what I am going to do it here, that suppose this is the graph of any function. This graph of course is a horizontal tangent a and b. According to Rolle's theorem, between these two zeros, you can take a and b here also, there are zeros of f dash x equal to 0. These are zeros of f dash x equal to 0. So these are for f dash x and these two are for fx. For fx root, you will find point of intersection with the x-axis. So there is a root of fx at this point and at this point. Other roots are there at this point as well as this point. So there are 4 points where the graph intersects x-axis. What does it mean? The equation has 4 real roots. It is obvious, we can see that this has 4 real roots. We take 1, 2, 3 that manner. It doesn't create any problem. But how do you state from the root of fx equal to 0, there is a root of f dash x equal to 0. This is again by the application of Rolle's theorem. Rolle's theorem only stated that between two successive zeros of polynomial, there is a 0 of its derivative polynomial. So we are not we are not going to find its derivative. Just we will remember this concept. Roots of f dash x equal to 0 are separated by roots of fx equal to 0. Am I clear? See, these are the points where fx vanishes. Take these 2 points first. Fx vanishes at these 2 points. Won't you get a point where f dash x equal to 0? So between two successive zeros of fx, there is a root of f dash x. Between two successive zeros of fx, between these 2 points, there is a root of f dash x equal to 0. So we can say that the roots of fx, suppose roots I am taking a, b, c and d, 4 roots. These are 4 roots of this biquadratic polynomial, not the graph of this thing. It doesn't matter. For that we have to take x equal to 1, 2, 3. Okay, whether we change it, you write this one x plus 1. No issue. You just take this one x plus 1. So coordinate of this point will be minus 1, 0. This point going to be 2, 0. This point going to be 3, 0. And this point is 4, 0. Now suppose at this point where it is x is 3.5 is f dash x 0. So there is a root. There is a root of f dash x between two conjugative roots of fx. This is another root of f dash x 0. There is a root between these two roots of fx equal to 0. Again there is another root between two roots of the given biquadratic polynomial. So one thing is very clear, the roots of fx are separated by roots of f dash x. So on the number line, if I tell you these are the roots of fx, then what does the roots of f dash x lies? This is for f1 at x1, this say x1, x2, x3, x4. Between two successive zeros, between these two there is a root, between these two there is a root, between these two there is another root. So these are roots of f dash x equal to 0. So at this point f dash x equal to 0. At this point f dash x equal to 0. So this is most important fact here. Roots of fx equal to 0 are separated by roots of f dash x equal to 0. So suppose there are n real roots. N real roots. N real roots means how many intervals can you get? N minus 1 interval. In each interval there will be a real root of f dash x. So can't I say that if there are n real roots of fx equal to 0, there are n minus 1 real roots of f dash x equal to 0? You can say that. Now if this thing is valid, in turn you can say that between two successive zeros of f dash x equal to 0, there is a 0 of fx equal to 0. You see, f dash x vanishes here, here there is a fx. Vanishes here and there, so there is x2 in between. There is a root of fx equal to 0 between two consecutive roots of f dash x equal to 0. So it is vice versa. Roots of fx equal to 0 separated by roots of f dash x equal to 0. At the same time, roots of f dash x equal to 0 segregated by roots of fx equal to 0. Alright. Now, to solve this one, all of you can say that fx equal to x plus 1. That is, if you solve these, the values of x coming to be what? X is coming to be minus 1, 2, 3 and 4. How many intervals they can form like this with two consecutive zeros? There are intervals like this. Minus 1, 2, 2, 3 and 3, 4. Okay. So these are actually not ordered pair, not xy form. These are roots of fx. How do you get roots of fx? By comparing it to 0. If you put this thing equal to 0, you are getting x minus 1, 2, 3 and 4. I showed you earlier. So if those roots are taken here minus 1, 2, 3 and 4 like that, then as I told you in the previous discussion, just today's only, that between two successive roots of fx equal to 0, there is a root of f dash x equal to 0. So if we split in three intervals, there will be three real roots here. One real root right between minus 1 and 2. One real root will lie between 2 and 3. One real root will lie between 3 and 4. That is R4. That we take as R4. Okay. R3. So there are three real roots and they lie in the interval minus 1, 2, 2, 3 and 3, 4. While answering this question in entrance paper, you just keep the concept in mind. Question may be made that manner where they can confuse you. But the thing is that between two successive roots of fx0, there will be a root of f dash x0. And between two successive zeros of f dash x, there is a 0 of fx equal to 0. So we can say that there are three real roots and they are lying in the interval, because they ask the interval, they are lying in the interval minus 1, 2, 2, 3 and 3, 4. Let us see next type of question where they have asked to find number of real roots of this equation. Now Rolle's theorem can be used to find number of real roots of equation like x cube minus 6 x square 15x plus 3 equal to 0. If you say that you can get it by factorization method only, that class 9 method, it's okay, no problem. But you may not get it always, because finding the first factor is not so easy. And if it is many degree polynomial, more than 5 or 6, then it is quite impossible to get it by factorization. Rolle's theorem is of great help in that case. So let us start with the easiest one. Find the number of real roots of the equation x cube minus 6x square plus 15x plus 3 equal to 0. So I'll just remind you the concept once more, that between two successive zeros of fx, there is a 0 of f dash x. So if these are the roots of the polynomial fx or fx equal to 0, then there is a root alpha of f dash x in between these two. F dash alpha will be 0. The second root f dash beta, beta with the second root, then f dash beta will be 0. Then gamma is the third root, you will get f dash gamma equal to 0. So alpha, beta, gamma, these are actually roots of what? These are roots of f dash x equal to 0. Okay? By using this concept, you can easily decide how many real roots are there. Let us start with part 1 by using Rolle's theorem. You take fx equal to x cube minus 6x square plus 15x plus 3. What about f dash x? This is going to be 3x square minus 12x plus 15. So this is x square minus 4x plus 5. Now, does f dash x equal to 0 has a real root or not? Let us check. If you put f dash x equal to 0, in f dash x equal to 0, we get x square minus 4x plus 5 equal to 0. What about the discriminant? Discriminant is 16 minus 20 minus 4. So there is no real root of this equation of f dash x equal to 0. So what will your conclusion about the original equation? Does it have a real root? And how many possible maximum? So we'll remember this concept, roots of fx equal to 0, those x1, x2, x3, x4, they will separate the roots of f dash x equal to 0. But these alpha, beta, gamma don't exist, because f dash x cannot be 0. Discriminant we are getting minus 4. Then what will be your conclusion? Your conclusion going to be this fx has only one real root. Because if it has two real roots, fx, if this has two real roots, in between two real roots, x1 and x2, there must be a root alpha of f dash x. But alpha doesn't exist. This equation doesn't have any real root. So x1, x2 also don't exist. So two roots or three roots of fx cannot be real. Maximum one possibility is there, and that will be that it must be a real root, because a cubic equation with real coefficient maximum 3 roots can be there. One of them must be real always. If imaginary roots occur, they will occur in pairs. So 2 imaginary roots will be there and 1 real root. So this one has answer 1. What about the next one? This is 4x cube. You can try the same manner. Let us do this one. Here f dash x is what? F dash x equal to 12x cube minus 24x square plus 24. Okay. So this is a cubic equation. We are avoiding calculation for this. We are better applying the concept what we have learned it for Rolle's theorem. According to Rolle's theorem, between two successive zeros of fx there is a zero of f dash x. But if people say that why not between two successive zeros of f dash x? Suppose this is f dash alpha and this is f dash beta. Can't I say that there is a real root of f double dash x? I mean second order derivative case. F double dash x is what? That is 36x square minus 48x minus 12. If you take 12 as common, it is 3x square minus 4x minus 1. So it has two real roots. Discriminant greater than 0, it has two real roots. If it has two real roots, they will separate the roots of this equation. I mean, they will lie in between roots of that equation. So it has three real roots. And this equation has all four real roots. So concept of Rolle's theorem is rich. We can find roots of any polynomial equation by remembering the roots of its derivative equation. There is another question of this kind. If a plus b plus c is 0, then show that the equation has at least one real root. How do you answer this kind of question? If a plus b plus c is 0, so that this equation has at least one root in 0, 1. So if we try to apply Rolle's theorem over there, we need to find a function whose derivative is this. Then our calculation will be easier. It means the fx1 will be always integration of this equation. So f dash x will be, we have to choose the function first, then we can approach this kind of sums. 2bx plus c. F dash x with this thing. Now fx can be obtained by integrating the expression on right side. Ax square 2bx plus c dx. If we integrate 3ax cube by 3, so write in the beginning ax cube plus bx square plus cx, and after integration there will be a constant d. Okay. Now we have to check whether we can use Rolle's theorem on this function or not. Then we can say that the derivative has a root. So the function you have taken, function is integration of f dash x, that is fx, and the interval is 0, 1. Now start writing here. Fx is a polynomial function. It is continuous in 0, 1. Number 2, fx is differentiable in 0, 1. And number 3, what is f0 here? If this is your fx, what is f0? And what is f1? Are they equal? Are they equal? Then Rolle's theorem third condition is obeyed. For f0 equal to f1, therefore a plus b plus c equal to 0. So under this condition only, which is given here, a plus b plus c equal to 0, we can show that f0 equal to f1. So all three conditions of Rolle's theorem satisfied. For which function? Ax cube bx square plus cx plus d. It is continuous, it is differentiable, and f0 equal to f1. Now what is the conclusion you are going to draw? That f dash x has a root between 0 and 1. Or after all these verifications, you will say that So f dash x has a root in 0, 1. F dash x is what? That is 3ax square this has a root between 0 and 1. Alright. So this way you can use Rolle's theorem to segregate roots of f dash x when fx known and vice versa. When f dash x known, you can find fx and roots can be predicted. So try all the sums. I'll be sharing worksheet problems with you. You must try it